Our next speaker is Joe Lasky from New Orleans, and he'll be speaking on Nelfinavir inhibiting myofibroblast differentiation.
I'd like to begin by thanking Luca and the organizing committee for all the hard work they put into bringing this wonderful program together and the opportunity to speak today. I'm more used to, could the timekeeper reset the game clock to 15 minutes here? I'm used to a 15-minute quarter, so this could run a little bit long. So the title of this talk is Old Dog, New Tricks. I hope no one will find a double entendre in this title regarding the presenter. It's about repositioning drugs as an antifibrotic, and in this case I'm going to illustrate with one drug, Nelfinavir, to illustrate the potential of off-target effects and weak effects as they may be. Let's see, I have to learn how to advance, which is this one? Yeah. So I'm beginning by showing a picture of Nelfinavir, and the reason I'm showing it is because the chemists will see that it's a very floppy molecule that can bend and twist and thus accommodate to binding by weak hydrogen bonds to various pockets of enzymes or kinases and such. And Nelfinavir is already being repositioned as an anti-cancer drug, so I want to reposition it as an antifibrotic as well. And it's been around for 15 years, so its patent's about to run out. The Nelfinavir has been shown to inhibit AKT phosphorylation, as well as many other things, as we're showing here, that may be involved. Many of us in the room have looked at as perhaps antifibrotic mechanisms by which this drug could work. And a lot of the work that has been done previously has been done in cancer cells, epithelial cells, including cancer cells from lung. And I'm going to show a little work today regarding fibroblasts. I'm not going to show you, though, that any human data showing that Nelfinavir cures this disease, but I'm fired up and ready to go if anybody wants to do that. So one of the concepts, as I showed in that slide, was that Nelfinavir can both be a proteasome inhibitor, but may also inhibit autophagy. And so it could be good, could be bad. On your right, we have the endoplasmic reticulum process of protease inhibition, which would be blocked by Nelfinavir. That conceptually could be bad. On the other hand, you've got this rescue phenomenon that's being upregulated here, this autophagy that was discussed yesterday. So just as a model, if we look at some data from what's been done in epithelial cells of cancer origin, if the Nelfinavir causes proteasome inhibition, then that leads to misfolded proteins, which could cause a phosphorylation eventually of this eukaryotic factor for translation, which globally will decrease translation of proteins, which possibly could be a good thing, but not entirely. There are selective translation increases, and so they show this model here where this is upregulated as a rescue mechanism when this is occurring. And then you get this phosphatase upregulation, which removes the phosphate from the tyrosine kinase. So it's always, I always think of the Karate Kid, it's phosphate on, phosphate off. It's both can occur to regulate the activity of this tyrosine kinase. And so here's some work that's done with fibroblasts. And so these are normal human lung fibroblasts. And what we're showing here is that with Nelfinavir and TGF-beta exposure, we're getting a reduction in alpha-smooth muscle actin expression over time, and also AKT phosphorylation, but not without the consequences I showed you in that earlier slide of a little protein, little stress, little ER stress going on. So my question that I have is, and I'd love to hear this in the comment portion of this talk from those who are much more knowledgeable about this than I am. Is this a deal killer here, or is a little bit of stress a good thing? All right. And so a little further work with these human lung fibroblasts just to illustrate that with Nelfinavir, we get a reduction in alpha-smooth muscle actin and collagen at the level of RNA as well as at the protein level as well. And you can see that the phosphorylation of AKT is involved here. We're not killing the cells at these doses. And in human beings, I think it's important to point out with AIDS patients, you might be in the 3-4 micromolar range. but you certainly can crank it up, and that's been done in the cancer patients as well. So these are very achievable levels for doing studies in human beings. One thing that we show here, though, in panel D is we have a specific inhibitor of AKT phosphorylation, and although we are inhibiting this here, we're not inhibiting as completely the alpha smooth muscle actin. So there may be something else going on as well as AKT that's being blocked by this drug. This is some work, because this has been discussed at this conference, that, well, this is done on plastic. How about if you put it in a three-dimensional matrix, and what would be the biological effect of doing these sort of things? And so here we have an assay of contraction, and it's shown on the right. What's illustrated on the left is that with TGF-beta, you get contraction of the gel, but with Nelfinavir, this is blocked. And Andy, I can already hear you thinking that, would this lead, because of the relaxation, to an increase in apoptotic cell death? And that's a good thing to think about, but we haven't done it yet. And so the alpha smooth muscle actin here then from these cells with TGF-beta alone is upregulated by TGF-beta, but even in the context of this three-dimensional culture with collagen, we get a reduction in that. So I said, well, maybe there's something else that's being inhibited as well by the Nelfinavir, and this is data just to show that SMAD2 and SMAD3 phosphorylation are being inhibited as well by Nelfinavir. And then the pi1, just to illustrate a downstream target of the SMAD2 and 3 phosphorylation, is being affected. We looked at what else could be involved or could be affected, and we found that SMAD7 really wasn't involved, because so many of these TGF-beta pathways were being involved, but at least not at the level of early on of SMAD7. There was maybe a slight increase, and this has been shown in the literature with cancer cells of PP2A being upregulated, and again, this is the phosphate off aspect of things. But in addition to that, oh boy, another one. P38, a MAP kinase, with the addition of Nelfinavir, it's being inhibited simultaneously with SMAD3 inhibition. And there's some literature to support that the MAP kinase P38 may affect, through the linker region, the phosphorylation of SMAD3 a little bit more than SMAD2. So those things are linked together. So this is getting a little incredulous that so many tyrosine kinase inhibitor, not tyrosine kinase, excuse me, so many single transduction molecules, kinases, are being affected by this drug. In addition to that, this is some data illustrating that the Nelfinavir in similar doses is causing an increase in autophagy. And this was discussed yesterday in the context of other molecules. But what we're showing here is that this phosphorylation of this mediator of mTOR is being inhibited by the Nelfinavir simultaneously with the decrease in smooth muscle actin, as shown above. And that's just an LCB3 ratio of 2 to 1, showing that at these levels, this is when you're overcoming and getting well above 1 in inducing autophagy by this drug. And this is just immunohistochemistry to illustrate that aspect of the LCB2 labeling here, where in the panel up here we've got a control. TGF-beta is decreasing the amount of that labeling, but with Nelfinavir you're getting these punctate increases in the one that's associated with autophagy. We also did some work, and this is the only work I'm going to show, with the myofibroblasts, because as we treat patients, we're treating people who already have myofibroblasts. And if we look to the right here, we can see that with Nelfinavir, there is a slight decrease in this collagen being produced. And then we're getting the addition of this extra band. In some of the older literature, these extra bands have been reported when autophagy is occurring, and these collagen trimers, as they get degraded, you see these bands. And we wound up doing mass spec on this, and this is the alpha-2 chain of the trimer of type 1 collagen. But also to show that if we inhibit the lysosomes with a bifidobacillin in the myofibroblasts, that you get an increase in collagen, showing that these cells are actively using this mechanism to regulate the amount of collagen that they're making. I don't have any animal model data with fibrosis with Nelfinavir at this point. At this point, all I know is that the animals survived the bleomycin. I'll see the tissue when I get back. But here's some other example of when this drug was used in another sort of fibroproliferative disease of sort, which is the monocrotaline model of pulmonary hypertension, and this is done in rats. And what they did was they waited 21 days after they got pulmonary hypertension in these rats after monocrotaline and then gave the drug. If you didn't get the drug, of course, your wall thickness got more, but with any of these protease inhibitors, but particularly with Nelfinavir, you got a reduction in that. And I haven't read a pathology report on my patients with UIP where they don't talk about that the vasculature is being involved as well. So this might be a little extra thing that could be done by Nelfinavir. And then, you'll never guess who is involved in this. If you guessed Annie and Moises, that's right. For once, I would like to publish something before you publish something with a new mechanism. But this is a protease. This is a different protease inhibitor called brimatinib. And what they have here is a saline control. With bleomycin, you get the fibrosis, and so they get a protection in these animals with bortezomib. A different protease inhibitor. It does not inhibit SMAD2 and 3 phosphorylation, though. So ours is does a little bit extra. So we got started on this because it was just a lunchroom conversation with somebody in the pharmacology department that, hey, you ought to try Nelfinavir because it's working well in these cancer cells. But subsequently, Dr. Z has published this computer modeling of looking at the structural proteasome and then doing binding comparisons with various drugs for off-target effects. And these are all hydrogen bonds, so they're weak effects, but they looked at binding free energy, which to me is just, it's like a miracle how this works. And then they come up with some sort of a network construction. And so this was just published, and here's what they came up with. That in the yellow circuits, these would be the nonspecific binding that would occur in all these different pathways. There's probably something in here for everybody in this room who's doing basic science on these things, but the pathways that would be involved and also the cellular effects shown here in pink that would be influenced by the nonspecific off-target binding of this drug. So there's a concept in the pathogenesis of disease that you have to get the disease, whether it be cancer or fibrosis, there's multiple nodes that are being affected, and there's redundancy in the system, and if you were just to block one of these nodes, it might find a way around, and the system might still be able to go on and have the untoward effect of malignancy or fibrosis. And so the concept here is that if you had a drug with a lot of weak off-target effects, but would bring things not completely to eliminating the activity of these kinases and phosphatases, but bring things back to a more homeostatic normal, that this might be a better avenue for treating these complex diseases such as pulmonary fibrosis. The other thing, as we were talking yesterday about heterogeneity, and I'm thinking about it got me to thinking, and Luis has warned me that that's a dangerous pastime for me. But I got to be thinking about off-target effects for the drugs that our patients are on and the polypharmacy they come in with, and this may help explain the heterogeneity of what we see as progression of disease as well in our clinical trials. So I'd like to thank the people who do all the hard work in the lab. It's a small group, but they're smart and hardworking. Taylor, Maggie. That is Professor Arnold Brody, and I'd like to thank Arnie because I never really have formally in any kind of a talk before thanked him. He was not only one of the early organizers of this meeting and got things going, and I thank him for that. But maybe 25, could be 30 years ago, he allowed a pulmonary fellow who didn't know which end of the pipette went into the solution to come into the lab and muck about, and gave me the opportunity to have a lot of fun over the years. So thank you very much for your kind attention.
We have time for several questions, including the other room, if there are questions from the other room.
Jeff snubbed me yesterday, so
okay. Joe, thank you. And, you've been a You've been a leader in this concept of using kinase inhibitors, and you did the Gleevec trial. So I'd just like you to expand these studies, which are somewhat in vitro, I guess, but your point about the wide specificity or the off-site effects being potentially useful in the context of a very complex disease like fibrosis. And if you take that back to the Gleevec trial, do you think, which according to the data at least failed, do you think that there were some weaknesses in Gleevec in terms of its specificity, and what would be the ideal kinase inhibitor that you would like to design and use in fibrosis?
I don't know what the ideal one would be, but I think I would like to get something that has multiple targets so that the fibrosis can't go around. We've all shown there's multiple pathways that we can induce or inhibit in order to cause fibrosis. In regard to Gleevec, it brings me back to the point that it's not what you don't know that hurts you, it's what you know that ain't so. And with Gleevec, the issue was that we didn't realize that patients with IPF make an acid glycoprotein that inhibits the activity of Gleevec. So I don't really think the trial crosses off BCR-ABL and PDGF inhibition. Just wish we were smarter when we started the trial.
So and that sort of begs the question, which is I think often the case, that we do a trial and then we discover stuff and wish we'd done the trial better, and that probably is true in settings other than just the one you're describing. But you'd like to see that trial done again, thinking about this idea of subgroups of patients and so on. Is that the message of what you've just said?
Well, I wouldn't be opposed to that. I actually like to see the trial done with this drug. And what I didn't bring up in the introduction is that as I was reading about this, and there's some support from the NIH and such for doing this type of repositioning drugs, that it takes 15 years to get a drug from concept into approval, and as much as $1 billion to get that to happen. So this would be a lot less expensive way to do that, and maybe on the tail end, in these days of limited resources in distributing health care, maybe a less expensive agent as well for 100,000 people in the United States a year.
Just repeat the question.
Yeah. I filed the provisional patent. That's as far as it's gone.
Yeah. Well, I mean, you have to do that, otherwise you've screwed the pooch today. And this is an important. You can extend this patent life probably get another 15 years.
It wouldn't be the first time I did the former, but point well taken. There comes a point though when you come to a meeting and you want to be able to say, here's a concept, and there may be other drugs out there, and we should think about this type of modeling in doing that. You're right.
It's the same thing we're after with the cells. Basically, we're trying to do everything with smart cells, and you're trying to do it with a smart molecule. And I think that's what you got to do, because nature is complex, and this disease is complex, and you just got to luck out, find something that does it.
It looks like we have a question from the other room.
Yeah, the question is actually more of a comment, Joe. I wonder if you can readdress again this issue of the specificity, because all of these kinase pathways, not only do they intersect, but they confer very, very different properties upon various different cells. So IKT inhibition on fibroblasts had a very different effect than in T cells and stuff like that. So the other aspect that I'm considering here is that is there a possibility that these protease inhibitors actually knock down the ability of these kinases to anchor? Let's say caveolin is now both in pulmonary hypertension as well as I guess in IPF, starting to become really, really a good target to be central in these pathways. So could there be anything that is not related to the kinase activity, but rather to the actual structure and the formation of these complexes? I don't know if I made it clear, but
Very clear, but it's a question, Luis, that I don't have the answer to.
okay.
Okay, there's no other questions. Thank you, Joe.